Hello, everybody. So what we're going to be looking at today is section 1.8 in your book, which is proof methods. So we already learned like some proof methods, right? So we already know, what do we know? Nothing. Uh, no, what do we know? We know direct proofs. We know proof by contrapositive or contraposition, as your book says. Positive. We learned about proof by contradiction. Was that it? I don't remember. Let's see here. Blah, 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 blah. I think that's pretty much it. I think. If it's not, it doesn't really matter. I think those are the three techniques that they taught, though. So in section 1.8, we just add a couple more. But actually, these are going to be simpler types. So this is going to be a short video, I think. Never right about that, but I think I'll be right about it this time. So in this lecture, we're going to look at proof by exhaustion. You get tired and you stop doing the proof. No, that's not what it is. We're going to talk about proof by cases. We are going to talk about, I think we're going to mention without loss of generality, which is something you read a lot in proofs. Generality, yeah, I spelled that right. Awesome, I think. Probably I didn't now because I said it out loud. Um, yeah, and I think maybe we'll do like an existence proof or something. Maybe we will. Uh, right, and yeah, so that's what we're going to talk about. So let's go ahead and get started. No point in waiting. And let's talk about a proof by exhaustion. So, or an exhaustive proof. Exhaustive proofs. So, what's an exhaustive proof? So, an exhaustive proof is a proof where whatever property you're trying to verify only has a certain number of cases. So, the property you want to show, you want to prove, only applies to a small number of cases. All right. So since the property you want to prove only applies to a small number of cases, instead of doing this in a general way, you can just actually check every single one of the finite small number of cases and show that each one has the property individually. So let me say that. So in words here, writing. So let's see. Property you want to prove only applies to a small number of cases. Um, so what you do, you actually write out every single case, not case, I shouldn't say case, but you write out every single, um, what are they called then? Not cases. I'm going to think of a better word while I'm scrolling up to where they talk about exhaustive proofs. No, they say cases. Oh, well, okay. So you actually write out every single case to show that the property is true. Okay. Now, there's not very many things that you're going to prove that are going to fall into this category, but here are some. So, like, here's their example. So this is book's example one in this section, and they say prove n plus 1 cubed is greater than or equal to 3 to the n if n is a positive integer within less than or equal to 4. Okay, so before we do the proof, I'm just going to make a comment. So my comment is this. N is positive and n is less than or equal to 4. So the only n values, that's what you're supposed to notice. The only n values that we need to check are what? Well, it has to be positive. So that means 1 or more. And it has to be 4 or less. So the only n values that are talked about here are 1, 2, 3, and 4. They have to be positive integers less than or equal to 4. So that's it, just 1, 2, 3, 4. So when you do a proof, you don't actually have to deal with this with n's in there. You can actually just put a 1 in there, put a 2 in there, put a 3 in there, put a 4 in there, and just check that the inequality is true. Okay, so that's all we're going to be doing here. So let's do the proof. Proof. We can just say we are going to verify the property, which is n plus 1 cubed greater than or equal to 3 to the n for n equals 1, 2, 3, and 4. That's all we're going to do. So you don't have to be clever about this. Typically what I'll do is I'll just, I say what I'm going to do, which I already did, and then I'm just going to write them out. So n equals 1. That's my first case. So I'm going to take this n equals 1, and I'm going to put it in to this equation. So we got 1 plus 1 cubed greater than or equal to 3 to the 1. And what I do when I'm writing these out is I shouldn't write it the way I just wrote it, because the way I just wrote it, it makes it look like I'm saying that 1 plus 1 cubed is greater than 3. But that's not actually what I want to do yet, because I haven't thought about it yet. I don't know if that's true. I need to check it. So if I need to check if something is true, I put a question mark over the symbol where I don't know if it's true. And then after I check it, then I'll take that away. So this is what we're checking. So let's work it out. So the next line would be like 2 to the 3 greater than or equal to 3. So that is 8 greater than or equal to 3. So I would put like a question mark over this one because I don't know if that's true. But then at the bottom, I see here that it's true. So true. Okay. And then we just do that for the other cases. So fit them in where I can fit them in. So let's put n equals 2 down here. So that is, what is it? 2 plus 1 cubed greater than or equal to 3 to the 2? Question mark. Don't know if it's true. So work out each side. So on the left-hand side, we've got 2 plus 1 is 3, 3 to the 3. So that is 27. On the other side, we have 3 squared, which is 9. So that's true. So true. Check n equals 2. So we just did that. N equals 3. 3 plus 1 to the 3 greater than or equal to 3 to the 3? Question mark. So what do we have? We have 4 to the 3, which is, I believe, 64. Greater than or equal to 3 to the 3, which is 27. Yep, that's true. And then we check n equals 4. 4 plus 1 cubed greater than or equal to 3 to the 4. Work it out. So on the left, we have 5 to the 3. That is 125. Greater than or equal to 3 to the 4, which is 81. That's also true. And there we go. So we just checked each of them. The property was, the inequality, and the inequality happened to be true in all 4 cases. And those 4 cases were the only cases that we were asked to check. So you just work out all the cases and you can say, we see that we proved that for integers n equals 1, 2, 3, 4. That's not how they worded it in the original, but that's just, I don't know, quicker for me to write. So we proved that that for integers n equals 1, 2, 3, and 4, n plus 1 cubed is greater than or equal to 3 to the n. Is that it? Yeah, that's it. And that completes our proof. All right. And that's what an exhaustive proof is. You just check. So there it is. So we just did an exhaustive proof. All right, let's see here. I'm going to look at the homework real quick. What do we have in homework? Oh, so long. Okay. An exhaustive proof. Yeah, you know what? I think actually that's going to be fine for exhaustive proofs. Let's talk about proof by cases, actually. So let's do proof by cases. All right. So even though we talked about cases on the previous proof technique, proof by cases is not really the same thing as proof by exhaustive. So what proof by cases is where the thing that you're trying to prove works a little bit differently for different parts of the numbers, if that makes sense. I know it doesn't, but so basically, you do a proof by cases when you need to, or it's just easier to split up, or I don't want to say that. It's easier to use different proofs or proof techniques even for different subsets. I'm going to say different parts of the proof. That's not really the best way to say it. This is not the best way to say it at all. Okay, but we'll see what I mean when I actually do one, which I'm going to do momentarily as soon as I scroll up to a proof by cases. Okay. Where is it? Proof by cases. Okay, yeah. So here's a simple one. So this is called example 3 in the book, section 1.8. And here's what we're trying to prove. Prove that n squared greater than or equal to n for all integer n. Okay, so that's what we want to prove. Now, why are we going to do a proof by cases? So the reason we want to do a proof by cases here is that this is true for all integers n. But with integers, sometimes like positive integers have different properties than negative integers and stuff like that. And so one proof might not work for every kind of integer. So what we want to do is split this up. So let me write that. So let's see, since negative integers have slightly different properties, than positive integers and also 0, it might, and it will, it might be easier to prove this for what we want to do is positive integers, negative integers, and 0. Or negatives, positives, and 0 separately. Now, it might not be easier to do it that way, but it might be easier. So if you think it's easier, then you can split it up. The point is, you need to prove it for all integers. So you can't just prove it for positive integers, and you can't just prove it for negative integers. You have to prove it for all integers. But you don't have to do one single proof for all integers. As long as you do positives and you do negatives and you do 0, then you've covered all of the integers, just not all at once. Okay. And so that's the idea behind a proof by cases. You think it'll be easier to split it up and do it piece by piece. So, proof. To make it easier, actually, it might not even be possible. We haven't even thought about it, but I'll say to make it easier, we will do separate proofs. That doesn't say separate. Separate proofs for in greater than 0, in less than 0, and in equals 0. All right. And those are our 3 cases. So let's try it. So how do we write it? You write it pretty much the same way as what we did up here for the exhaustive proof, right? We had 4 cases, n equals 1, 2, 3, and 4, 4 specific cases that we checked. Down here, we are going to have 3 different cases, but they're not specific numbers, right? We still need to use n as n, but we'll know that n is positive or n is negative or whatever while we do it. All right, so let's try this. So case 1, and you don't have to say case 1, but I just am. So case 1, let n equal 0. Let's do the n equals 0 case first. Okay, we want to check. What are we trying to prove? We're trying to prove that n squared is greater than or equal to n. We want to check n squared greater than or equal to n. That's the property. So we're just, in this case, put in a 0, right? Because we're checking n equals 0. 0 squared greater than or equal to 0? Question mark. Well, that's 0 greater than or equal to 0, right? And of course, that's true. All right, done. That's what we needed to do for that case. Now let's do the case where n is positive. And again, you don't have to number them. You could say like case n equals 0. All right, you could write it like this. Case n equals 0. Or you could just write n equals 0. It's up to you how you do that, as long as you make it clear that you're splitting it up. So I think I'm making it clear, right? Case 1, case 2. What's case 2? Let n greater than 0 be an integer. Okay. So it's an. All right. So what do I got? I got a positive integer now. Okay. So what I want to do is, what are we doing? Oh yeah. Yeah. So let's actually erase this. So here's why I don't like it. So the idea that I had for this proof was this. What I wanted to do for this proof was I wanted to multiply both sides by n, and from this. So if you take what I circled and you multiply both sides by n, if you multiply the left side by n, you get n squared. If you multiply the right side by n, you get 0. However, that's not what I'm trying to prove. I'm trying to prove, up here what's circled, I'm trying to prove n squared greater than or equal to n, not n squared greater than 0. I want n squared greater than n. I want an n here. And you can't do that with a 0 because when you multiply by 0, you still get 0. And so it didn't work, right? But I kind of wrote this case wrong, right? This is not actually what I should have done because here, like this was the n equals 0 case. So n equals 0 is already taken care of. We already proved that. So if n is greater than 0 and it's an integer, then actually n is actually greater than or equal to 1, right? Because that's the first integer that's greater than 0. So what I should have done is, first of all, erase this. We're going to rewrite this, but this is actually slightly wrong here, isn't it? Right? I shouldn't have said n greater than 0. I shouldn't have said it this way. I should have said n greater than or equal to 1. And n less than or equal to 1, and n equals 0. Right? That's actually the three cases for integers. Integers bigger than 1, integers or bigger than or equal to 1, integers less than or equal to 1, and 0. That's it. So if I make that change here, I think my proof will work out. So let n greater than equal to 1 be an integer. Okay? And now we're going to try that strategy that I just said. We're going to multiply both sides by n. And I don't really need to, but I'm going to kind of be precise about this, right? So I put an n on both sides, and then on the left-hand side, n times n is n squared. On the right-hand side, 1 times n is n. So we've got n squared greater than or equal to n, which specifically was what we were trying to prove. That was it. Okay, so that's what we're trying to prove. So that's done. Okay, so we finished case 2. That's all we needed. And you see how that was easier because we were only looking at positive numbers there. Now let's try case 3. So case 3 is going to be the case where n is going to be less than or equal. Oh, sorry, this is dumb. Still dumb. Less than or equal to -1, right? Positive numbers and negative numbers. I don't know why I put a 1 there. Sorry about that. So case 3, we're going to have let n less than or equal to -1, right? The negative numbers, negative integers, be an integer. And we're going to try the same method that we just tried. So we're going to multiply both sides by n. Okay, so we're looking at this, and then I'm going to do it. And there's a reason why I rewrote it. So sorry if you don't like that. Okay, so we're going to multiply both sides by n. So on this side, we multiply by n. And on this side, we multiply by n. But think about what happens to the middle here. This is an inequality. If you take an inequality and you multiply by a negative number, which n is a negative number, if you multiply by a negative, this symbol here flips and is going to point in the opposite direction. So this is actually the wrong way around now. It should be going the other direction. Okay? So now I've got n squared is actually greater than or equal to negative n. Is that true? Is that what we wanted? Hold on a second. Sorry, fair squeaky. We wanted n squared greater than or equal to n. Right now we have n squared greater than or equal to negative n. Oh yeah, this is actually, okay, this is, okay. So this is fine, but I'm gonna rewrite it so I can scribble on it again. So we have this. Let's think a little bit about this number here. This number right here, negative n. What can we say about it? What we can say about negative n is that it's positive, right? Because n is negative, so that means negative n is positive. So this is a positive number, right? And if it's a positive number, every positive number is greater than every negative. Does that make sense? Every positive number is greater than every negative number. So if negative n is a positive, it's greater than every negative number. So I should just be able to take this and say, well, n is negative. So this inequality that I just wrote down is true, right? I think it is. So let me see if I can move stuff around a little bit. That up, that up. Just trying to give myself a little bit more space on the page. Okay. So we can add that extra greater than or equal to n on the end here. And that's valid because this is a negative, and any negative is less than or equal to any positive. All right. So what do we conclude? N squared greater than or equal to n, right? We're going to be looking at just this and this. That's the only part we need. We don't need that negative n part in the middle. So we get n squared greater than or equal to n, which was, again, what we were trying to prove. So look at what we did. We proved it for positive numbers. We proved it for positive numbers up here. We proved it for, we proved it for 0 here. We proved it for positive numbers in case 2. And then we just proved it for negative numbers in case 3. And notice that, case 3 relied on properties of negative numbers, right? Like the inequality, like had to flip around. And then we had to add this extra bit here on the end that we did not have to do for positive numbers. So how would you have combined cases 2 and 3 and done them all at once? I don't even know. So that's why it makes sense to break it up the way we broke it up. And then once you've done all your cases, we can just say, well, we've done it for all integers now. So let's see. So we verified. So we can say, therefore, n squared is greater than or equal to n for all integers. Integer n, right? Because we checked all the possibilities. Okay, and then that is what we call a proof by cases. Okay, so let's see if we can find another one or something. Let's see, looking for one in the homework set. I don't like the one that's in the chapter. Um, let's see. I don't know. I don't see anything that looks good. I think what I want to do actually, maybe, do we want to go back? What time is it? We've done a half an hour. The video's not as short as I thought it was going to be. Um, all right, so let's just move on, and then we'll come back maybe and see what we can do. So the next thing I want to talk about is without loss of generality, which is not a proof technique, but it's an idea. And I'm putting it in quotes because it's a phrase that you say without loss of generality, blah, blah, blah. So what is this? Um, so when, um, let's see, here. When a proof, let's see, has several numbers like variables, multiple variables, and it doesn't matter which one is which, they're just names. You don't want to have to repeat the proof for like a bunch of times in a row, depending on which variable is which. So if you have a proof that has multiple variables, it doesn't matter which is which, um, you can avoid repetition by stating without loss of generality, and then you say like you say without loss of generality, assume something, and then hopefully that something is going to give you fewer cases that you have to look at specifically. So without loss of generality, or you'll even see like they do it so much in some books that they just write like the abbreviation without loss of generality, WLOG, without loss of generality. Um, and then whatever you're assuming to make your workload lighter, to make the proof less work. Okay. Now, when can you use without loss of generality? So you would use without loss of generality for something like this. So let's see. So I don't want a specific example here because I want to talk about the idea first. But like, say you had like prove property P hold for um, X and Y, where X is not equal to Y. Okay. Now, that's just like, let's say that that's a proof that you're trying to do. I'm saying this is an example, but we don't know what property P is, so it's not actually a thing we're going to prove. But let's say I have a property I want to hold for X and Y, and X is not equal to Y. Well, maybe my proof, suppose further, so this is just kind of extra information, suppose um, it matters for the proof which one is positive and which one is negative. Or sorry, not negative and positive, but it matters in the proof which uh, is larger, X or Y. Now, why does it matter? I don't know, right? That depends on the specific math. But like, it matters which one is the biggest. Then what technically you would have to do is um, your proof might have to be like this. Would have to be in cases, right? Because if it matters which one's bigger, then you would have to split this into two cases where you say, like, case one, uh, let X be greater than Y. And then blah, blah, blah. You do your proof, right? And then you would also have case two, let Y be greater than X. And then you do your proof. Okay. But wouldn't those two cases probably be exactly the same? Like there's nothing special about X and there's nothing special about Y. It's just that for whatever reason, you need to know which one's bigger in order to complete your proof. Well, then you're really just writing the same exact proof twice. Just in case two, the work would all just have all the X's and Y's switched around, right? So case two, it would turn out the same proof, the same exact proof as in case one, except X is and y's would just be switched. That's a waste of time. That does not look like it says time. Better, kind of. All right. So that would be a waste of time to actually have to do the entire proof twice, just to consider the cases separately where x is bigger than y and where y is bigger than x, when it doesn't matter which one's x and which one's y. So to save work, to avoid that wasted effort, you would say, like proof, you'd start your proof, and then you would just say, without loss of generality, I'll abbreviate it. No, I won't. I'll write it. You would say, without loss of generality. I'm going to remove this actually. Don't like the way this needs to be on the second line. So normally it'd be a good idea to state why you were doing without loss of generality. So we could say like this. You could say, we know either x greater than y or y greater than x. So without loss of generality, assume x greater than y. And then you do your work, right? And then you go proof, 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 and then you're done. Okay. And then that way you only have to do the proof once. Because when you say, like, these are the two things that could happen, and when you say without loss of generality, assume x greater than y, you're saying it doesn't matter which one is which, right? You're saying the two cases are the same, and you're just going to do one of them, and the other one's the same, but reversed. Okay. So the claim is when you do this, um, x greater than y and y greater than x are the same proof. When you do that. Now, that better be true. Okay. If it's not true, then when you say without loss of generality, then you would be lying. You did lose generality, right? So when you say without loss of generality, you're saying that you're not, like, what you're claiming is you're only going to show part of it, but you're really doing the whole thing because the other case didn't matter. The other case was the same as the case that you did, really. So that's why the generality is not lost, even though you only did half of it technically. Okay. So that's the idea, but that's not a proof. Let's actually do a proof, maybe. So let's see if we can find one. Okay, yeah. Okay, so here, let's just do the one in the book. So their proof is this. Example 7. Okay, so what we need to prove is if x and y are integers and xy and x plus y are even, then both x and y are even. Okay, so before we get to doing the proof, I just want to like write this out kind of in symbols a little bit. So there's a lot here. So I'm going to skip over this part. X and y are integers. We know we're talking about integers now. But basically you have if x, y, and x plus y are even, and then you have a then both x and y are even. So it's basically this, right? It's x, y even and x plus y even implies x even and y even. That's the structure of this. And we know that they're integers, but I don't need to write that right here. So that's what you're trying to prove. And remember how we did the proofs in the previous section? We didn't like having like something complicated like this on the left-hand side that's harder to deal with. We liked having something like this on the left-hand side. So this is a case where you would want to do the contrapositive. That has nothing to do with without loss of generality. It's just this is a proof that you would normally do with contrapositive. So the contrapositive, remember, you switch the order and negate them. So it'd be not x even and y even implies not xy even and x plus y even. Right? So that's the contrapositive. But then we have this kind of structure, not P and Q. And remember what De Morgan's law does there. What does De Morgan's law do? It when you distribute a negation across an and, it turns into an or. So not P or not Q. So we need to change these to ors. So this is going to be not x even or not y even implies same thing here, not xy even or not. I don't know why I'm writing the word or instead of the symbol, but whatever. Okay, so you have that. But then we know that not even means odd. So we have, when we write this out finally, we have x odd or y odd implies xy odd or x plus y odd. Okay, so all of that was the like figuring out what the contrapositive is. And then that's before we do the proof. And then this right here is actually what we're going to prove. Okay, so this is the contrapositive and it's what we want to prove. All right, so this is what we'll prove. Okay, so we'll do this. Okay, so now that we know what we want to do, all right, so let's do our proof. Okay, so we got let x and y be even. No, that's not right. Sorry. Let x and y be integers is what I meant to say. And without loss of generality, I'm going to make an assumption. You know, I want to write that a little nicer. So let x and y be integers, and what do we need to assume? One of them is odd, right? Now, which one's odd? Is x odd or is y odd, right? X is odd or y is odd. Which one needs to be odd? Well, it doesn't matter, right? So, since it doesn't matter which one's odd, then we can just pick one and it might as well be X, right? It doesn't matter which one's which. One of them's odd. So we just say without loss of generality, assume X is odd, right? And that way we don't have to do one proof for X odd and one separate proof for Y odd. We only have to do one of them. Okay? So let us go ahead and try to do this then. Okay. So Since x is odd, we can say x is, let's say, 2m plus 1. Can we do an n? Do we need an n? Yeah, let's do m. That'll match the book. So let's say x equals 2m plus 1 because x is odd. Okay. Now, then what we need to do is a proof. But what we need to do is what? We need to show xy is odd or x plus y is odd. But which one of those two things that I highlighted is true might depend on whether y is odd or not. So we know x is odd because we said, uh, without loss of generality, assume x is odd. But now we don't know whether y is odd or even, right? One of them's odd, x, but the other one we don't know. So it could be odd or it could be even, and it might matter for the proof. So now we do a proof by cases. So we're going to do case one. Case one. Let's do y is even. Okay? So y is even. But we also know that x is odd. So we already have that. So y is even. So y is actually not is equals. If y is even, then y could be 2n, right? And I should have set that up here, but for integer m, some m, and down here we have for some integer n. Okay, so now what we want to do in case one is we want to figure out what's happening here. Uh, I think this is what's going to end up odd, right? So we can just say x plus y. So then x plus y is what's x? X is 2m plus 1 plus y, but y is 2n. So x plus y is this, which is 2m plus 2n plus 1, which is 2 parentheses m plus n plus 1. Hopefully you can see that that's odd. So I could say like 2p plus 1 for integer p, which is going to be m plus n, m plus n. And so x plus y is odd by definition. All right, so that was what we needed to verify, right? One of these had to be odd. And in this case, it was x plus y. Now, what about the other case? Let's do case two. So in case two, y is going to be odd. And so what's going to happen there is when y is odd, probably this is the one that's going to end up happening. Probably x times y is going to be odd. So now why is that true? I don't know. I just figured that's how it's going to work. You could check them both, but one of them has to be odd. So let's try it. Try this one. So y is odd. What's that mean? It means y is 2 times something. Now I could maybe use the same in. I could, yeah, because this is a separate case, so it's okay to reuse the variable names now. So y could be 2n plus 1, or some integer n. And let's work out what xy is now. So x times y is x, which is what? 2m plus 1 times y, which is 2n plus 1. Multiply that out. I think we've actually done this before. So multiply this out. It's going to be 4mn plus 2m plus 2n plus 1 when you FOIL it out. We can factor out a 2 out of those first things. 2mn plus m plus n plus 1. And that could be 2p plus 1 for an integer. 2mn plus m plus n. So it's odd. So xy is odd. Um, So that means we did these cases here, but those were all of the cases now. So in first one, x plus y is odd. In the other one, x times y is odd. So in either case, this entire thing was true. So I think we did it. So once we think we did it, we can just write. So if, let's see, what was it? If x or y is odd, or y is odd, then xy or x plus y is odd. Therefore, the thing that we actually wanted to prove, which was the contrapositive, so therefore, if xy xy and x plus y are even, then x and y are even. I almost forgot what we were trying to prove, right? Had to go look it up. But we proved the contrapositive of that. But, once we proved the contrapositive, we proved the original. All right. So let's talk about without loss of generality again. What did without loss of generality get us? What without loss of generality got us is fewer cases. So we did case one, right? Case one. So basically we did this. Let me write it. So basically we did case one, but case one was x odd, y was even, and case two was x odd, y odd, right? And so in both of those cases, x was odd. If we hadn't done the without loss of generality, we would have had to consider every possible combination. So without the WLOG, which I'm not going to write again, but without that, we would have had to do the two cases that we did, which just realized I can just cut and paste them. We would have had to do those two, but those are not the only possible cases because we would have had to consider every case where one of them was odd. So we would have also had to consider the case where x is even and y is odd. Is that the only extra one? I guess that's the only case because what we actually ended up proving was x is odd or y is odd. So this is all of the ways that one of them could be odd, right? There's no case four because case four would be even, right? But that didn't have anything to do with what we had to prove because we were proving something about when one of them was odd. So it would have only been one extra case if we had skipped the without loss of generality. Without the without loss of generality, we'd have had to do every case where one of them was odd. And we could have done it. It would have only been slightly more work, but, we saved work. Sometime with the without loss of generality. All right, and that's what it's for. It's just, it didn't matter which one was odd, so we just said, let's make sure it's x. Okay, yeah, I think that's going to be it for this section. So you're going to see in the homework when I post it that you do not actually have to do a bunch of questions from section 1.8. They're mostly from 1.7, But cases and exhaustive proofs are important. So good that you understand this logic. Also, I'm going to remind you again. I know I said it in the 1.7 lecture as well, but when you're proving stuff, you should really copy the way that I write them, unless you have a good reason not to. Like if you really hate the way I write something, you can write it in a different way. What you cannot do is skip a lot of the words. You can't skip all these words here. Okay. When you're writing a proof, I'm going to write this. When writing a proof, it has to be readable. It's not like a math problem that you're working out. Proofs are not computations, right? They are arguments you are making with words. Okay. You cannot skip the words. I mean, you can use mathematical shorthand for the words, but you don't really have a big mathematical symbol vocabulary at this point. So you can't skip the words really, or the structure of a proof. It won't be a proof if you do. Okay. So yeah, that's my piece on that. So you should really be copying the way I write them for the most part, unless you have a good way to write it that's slightly different. But it should not be more than slightly different. It won't be very different. Okay. Um, anyway, okay, enough of that. So that's it for this lecture, and I will see you next time.